Hey everybody, Mr. Troy here. I don't know about you, but this is an interesting time of year for me, right? Things speed up, things slow down. So we have to stop and kind of take stock and grab ourselves a delicious lemon LaCroix, listen to the wind outside, look at our dog napping in the other side of the room, and just enjoy. It's time for math with Mr. Troy. I didn't mean for that to rhyme. Pretty happy about it though. Alright, so the first part of this is a continuation of the work that we did in our last lesson on the rational roots theorem. It'll all tie in, I promise. So if you haven't watched that video yet, go back and watch it. It's extremely important. We got about halfway through, actually 1/4 of the way through, this problem right here. Okay, so if you need to refresh yourself on it, take a look at it, see what we've done. So this is where we were at. We had taken this rather large polynomial, and we were able to break it down to this. The plus 0 up here right above my head is because we found that there was no remainder, but we don't need to write a plus 0. So now what we're going to try to do is we are going to try to break up this set of parentheses. And the way that we're going to do that at first is we are going to use this rational roots theorem. So we are going to look at the factors of 42 and see if any of those work. The reason it's the factors of 42 is because our lead coefficient is 1, which means we don't have to worry about the q's part of the p's over q's. Okay, so I wrote down all of the possible rational zeros, and I'm just going to start plugging them in to the synthetic division or synthetic substitution, and what I want to get is a remainder of 0. Now, there are certainly tricks or things to notice that would tell you, for example, that 1 works or that -1 works. We'll learn those in due time, but for now, we're just going to plug things in, and this is a process of guessing and checking. So my first guess is going to be 1, because why not? 1 is easy. So when we plug in 1, we multiply by 1, and we can tell pretty quickly that this is not going to work because we didn't end up with 0 here. Whap, whap. Okay, so when that happens, we cross off +1, and we can try -1. So that's going to change everything after here. And we'll see if that one works. You should be able to tell pretty quickly if it's going to work. And I don't think so. I got 72. Now, are there things that are true about the answer you get out, or the signs that you see in here, or the signs that you see in here? Yes, there are things that are true about that. But we are not going to worry about those right now because we've got a process and we can follow the process. You can kind of move around however you like. You don't have to go in order. Do keep track, though, of the things you've tried. So say, for example, I want to try -3. So I plug that in, and I get not the right answer. I just want to make sure that I cross out -3 in some way so that I know that I'm not on the right track. So at first you can find this really frustrating because it is this kind of approach of just ruling things out. But that's okay, you know, like we got time. You don't need to worry about it too badly. The cool thing is when you notice that something is going to work. Maybe you notice like right about here. Oh, cool. So it does work. So here's what we just figured out. That this that we were trying to factor has x equals 3 as a 0. That means x minus 3 is a factor, and this quotient is the remaining part of that. So that's x squared plus 5x minus 14. Well, I know how to factor that. I don't even need to use the p's and q's and whatly whatnots, because I just know that that's x plus 7 times x minus 2. We include the original factor that we were given, and we have a complete linear factorization. Then we go back to the directions, and we say, did it ask for zeros, did it ask for factors? It asked for zeros, so we're going to convert all of these answers from zeros to factors. So all of the solutions, or all of the zeros for this function, are -7. That's not a 7. -7, and 2, and 3, and 5. Now, it should make sense that if I take these 4 x's and multiply them together, I'm going to get an x to the 4th, which gives me 4 solutions. There's actually a name for this. It's called the fundamental theorem of algebra. You know it's a good day in math class when you are learning a fundamental theorem. Okay, so the thing you need to take away from the fundamental theorem is this. If the degree of an equation is 4, you're looking for 4 solutions. If the degree of the equation is 3, you're looking for 3 solutions. If the degree of the equation is 17, you are looking for 17 solutions. Okay? That is the long and short of it. Now, there's a bit more that we have to add on to that. That this is about complex solutions. So one of your solutions could be, 3i or -3i. That would count. Okay? Also, sometimes solutions are repeated. So if we look at this equation, we see that it's x to the 4th. The fundamental theorem of algebra tells us that that means it has 4 solutions, 4 factors, 4 zeros, however you want to think about that. But it doesn't say that it has 4 distinct zeros. So this has what's called multiplicity 2. So what is its multiplicity? Its multiplicity is 2. Because if we wrote this out as all of the factors, we would have to write that twice. That's what that squared means. All right, so the fundamental theorem of algebra says that the number of solutions to a polynomial equation is its degree. Those solutions might be real or imaginary. They might be repeated, but whatever your lead coefficient or what your leading term's exponent is, that's how many solutions you're looking for. Okay, one interesting thing to kind of plug in on top of this. Whoa, whoa! Whew. Okay, well, here I am now. One interesting thing to plug in on top of this is that complex zeros occur in conjugate pairs. So if I tell you that 3i is a solution, then that implies that -3i is a solution. If I tell you that 2 minus 7i is a solution, that implies that 2 plus 7i is a solution. Now, this is only true if the polynomial actually has real coefficients. So like this, where it has an I as part of its coefficient, wouldn't have complex conjugates like that. But we're never going to deal with anything like that in our class, okay? That would be rare, or it would be a bonus question or something like that. Okay, so I want to show you a way that some of this shows up in your web assign. So for example, this says find all the zeros of the function. If you are looking at a quadratic, you don't need to mess around with any fancy stuff. You can just put that directly into the quadratic formula. If it factors, you can factor. If you love completing the square to factor, you can do that. But you always have a way to do this type of problem. Okay, so opposite b, plus or minus the square root of b squared minus 4 times a times c all over 2a. So when I'm finding the zeros, remember that means I'm looking for the x values that will punch out 0, or they'll give me an output of 0. And these are going to be imaginary. So negative 14 plus or minus the square root of 196 minus, what is that? 212? Sometimes I really struggle with my addition and subtraction of positive and negative numbers and stuff like that. Makes me feel silly, but that's okay. There's always room for us to improve. So that gives me negative 14 plus or minus, the square root of negative 16 all over 2, which is negative 14, I'm getting ahead of myself, plus or minus 4i all over 2, which gives me negative 7 plus or minus 2i. Okay, there are other ways to do that. But as soon as you have your zeros, you can get factors really easily. This doesn't take any extra work or anything like that. You just do x minus one of the zeros and x minus the other 0. The thing that always trips me up is that, like, when I distribute this out, I'm going to get x plus 7 minus 2i and x plus 7 plus 2i. It kind of throws me for a loop for a second because I'm expecting these to be different as well. And they're actually the same as each other. It's the i's that are going to change. Okay, so a product means multiplying them together, and linear factors mean that they would start with x, as opposed to x squared or whatever. Okay. If you are interested in seeing how to do this without using the quadratic formula, I recorded a video called Factoring Using Complex Numbers. I probably won't remember to put in an annotation, but if I do, click here. I've never done this before, so I don't actually know if that's going to work. But remember to like, share, and subscribe, okay? And ring the bell for notifications. Okay, the big thing that we are going to be doing, like what we're leading up to in this unit, we're going to start with right here, okay? It's going to give us a big polynomial, and it's going to ask us to write it as a product of factors that are irreducible over the rationals, linear and quadratic factors that are irreducible over the reals, and in completely factored form, or all linear factors. So let's start with part A. This video is going to go on for a couple more minutes, so now would be a great time for you to pause, take a stretch break, and yeah, just kind of relax a little. Okay, so we have no information about this other than the fact that it has all real coefficients and it ends with a -25 and it starts with a 1. So when that happens, you have to start with your p's over q's or the rational root theorem. So remember, that's plus or minus factors of 25 over factors of 1. 25 from here, 1 from here. So our possible things to plug in are plus or minus 25, plus or minus 5, plus or minus 1. So there's only 6 things to plug in. That's great. Okay. I'm going to start with 1. So I'm going to write out my coefficients. And I'm just going to try 1. And this part's pretty quick, if you do it right. Okay, that didn't work. 1 does not work, so we're going to cross off positive 1. Whoa, hey, get back here. Okay, let's try negative 1. Hey, that works. Okay, so that means that we got x plus 1, that's this part right here, times x to the 4th minus 4x cubed plus 20x minus 25. Okay, now the place where you go from here is to continue on and do synthetic division with these numbers. So these new coefficients can go straight into some new synthetic division. We don't need to use the 0, though, because remember that was just a remainder. So, say I want to see, does -1 work again? I know 1 doesn't work because it didn't work for the big equation, but maybe -1 works again. Let's see. It's close, but not quite. So with that, I can cross off -1. I'll change this, and now I'll try -5. I already had the negative there, so that's why I'm trying -5. And when I plug that in, I can see kind of quickly that that is not going to work. Like, I don't even need to get this far to be like, whoa, that's going to be a big number. So -5 is not going to work either. The way that I could tell is I just knew that it wasn't going to equal 0. All right, so let's try +5. You'll notice in the coefficients if the numbers are going to be like especially big or especially small after you've done about 1,000 of these. So it'll make it a lot easier to check. Okay, again, our numbers are way too big. This is not going to equal 0. Uh-oh. Our only option left is to try 25. So I'll try positive 25 first. And I've got my doubts, but you never know. Oh boy. 21 times 25. Hey Google, what's 21 times 25?
The answer is 525.
Okay. I know some of you were shouting that at the screen to me because you know how to do your multiplication facts. So this number is going to keep getting bigger and bigger and bigger. So 25 is not going to work. Maybe we try negative 25. Okay, 25 times 29. I forgot you're not supposed to say the smart commands in your video, because then you could say, like, order me a pizza or whatever, and then, you know, or order my merch off of mrtroymerch.mathbiz or whatever. Yeah, so this one's not going to work either. The numbers are just getting way, way, way too big. And what this means is we've tried all 6 of our possibilities, and none of them work. So these are all of the rational zeros that are possible. Okay, so then the next thing we would want to do is it says linear or quadratic factors that are irreducible over the reals. So, is there a way to use irrational numbers, which are still real numbers, to factor this? Then, the last step, in completely factored form, is there a way to factor using complex numbers? Okay, I'm actually going to do all the rest of that in this video, but it is something that you do not need to know until next week's WebAssign. So if you want to leave now, that is totally fine. And if you just find that interesting, then I'll see you for the next little bit of the video. All right. Thanks for watching. Have a good one. If you want to hear the theme song, just go back to the beginning of the video. All right, cool. Do you think they're gone now? Okay, so only the true math real believers are here, right? So if I wanted to factor this, it says using quadratic and linear factors. I know there aren't going to be any rational linear factors. And the reason I know there aren't going to be rational linear factors is because I just tried all of them and none of them worked. So I'm going to try some quadratic factors to see if that works. I'm going to start with an x squared and an x squared. And I'm going to try a plus 5 and a minus 5. Now, you may be saying to yourself, but Mr. Troy, that makes x squared, or x to the 4th minus 25. Where's the other stuff coming from? Well, I'm going to try and put a middle term in one of these and see if I can't figure out a way to get that other term there. So I'm going to look here and I'm going to say I could get a 20x if I multiplied this plus 5 by a plus 4x. Well, what would that give me? X to the 4th plus 4x cubed. Oh, that's kind of right. I want a 4x cubed, but I don't want it to be a plus 4x cubed. You got any ideas? Oh, right, good. We could do this like it's like a Blue's Clues or Dora the Explorer, where you're like, a clue, a clue. Or the map. And yeah, you're right. I could just move that 4x to the other side. So I'm going to put this as a minus 4x on the other side. And that's going to give me minus 4x cubed. And then minus 5x squared. I did that out of order. My goodness, how terribly confusing. Let's look at it again. Okay, x to the 4th minus 5x squared minus 4x cubed plus 20x plus 5x squared minus 25. Middle terms cancel out, and I'm left with x to the 4th minus 4x cubed plus 20x minus 25. Woohoo! That's exactly what I was looking for. Okay, now, how in the world does that help me factor this irreducible over the reals? Well, a real 0 of this is root 5. All right, so now I've got this down to 3 linear factors that are real numbers, and this must give me imaginary numbers. Oh, we got like 30 seconds left. So then from here, all you have to do is figure out how to factor this. Well, that's pretty easy. I mean, it's x plus 1 times x plus root 5 times x minus root 5 times x minus 2 minus I times x minus 2 plus I. Hey, that's it. We've got it. It's in completely factored form. If you made it this far, you are a true mathematical person. Rats! I thought it was going to come to me. I thought I was going to have some sort of like great... Anyways, thanks for watching the video. Thanks for watching the extended bonus features at the end. And y'all, have a good one.